Hello and welcome to Big Data Analysis with MongoDB and Neo4j. My name is Faisal Izhar and I am Masters of Science student at Macquarie University. Project overview. Our project was to develop and demonstrate a comprehensive big data analytics pipeline using MongoDB and Neo4j for two distinct use cases. For social media analytics, we uncovered trends and coordinated activity in a Twitter-like dataset using MongoDB, and using Neo4j, we created a fraud detection model identifying fraudulent patterns and suspicious network structures in a financial transaction dataset. So initially with the data curation pipeline, we started with cleanup and we used two Python scripts to clean the data, to skip the recommended lines and remove the unwanted fields. And then we ran an ingestion pipeline, which parsed stray JSON tweets into tweets clean and users collection. We extracted the info and we also added the right fields. We deduplicated data by tweet ID and then we upsetted the users. We implemented MapReduce to process the large data set. We also created indexes following that ESR rule. Index justification. We created the index using the ESR rule, that is equality, sort, and range, to align with the query execution patterns. Indexes are designed to optimize frequent Twitter analysis queries. In the assignment, the indexes reduce full collection scans, it enhances query performance and aligns with the analytical tasks. So we had three initial problems. We had to identify hashtags showing the week or week increases. We followed these following steps and we computed the growth rate by dividing week 2 count by week 1 count. But unfortunately, we couldn't get the result because all of the time, original data set was very clustered and we couldn't find any data and that could support our query. So we uploaded the as a random date during the ingestion script, and we put a 70% bias towards recent 14 days for realistic activity. Then here's the output that we got after adding that. So the next, a coordinated link burst. We detected potential coordination when multiple users share the same domain quickly. We collected the distinct users and sample tweet IDs, and here's the result that we got. Coming to the next question, high value. We detect spam-like users posting identical content repeatedly. We ran this following query, but we ended up getting no results. Why? Because our data set has 10,000 tweets that is spread across 60 days. So there is very low daily repetition, and most duplicates were retweets shared by different users. So when we cleaned the text, it became blank. So our query logic was correct, but lowering the threshold or normalizing text would show more results. Next, we come to the next part, that is soft puppet signals to detect the fraud. Scammers. So our goal was to detect pair of users sharing the same location or profile domain and using 3 common hashtags within the 24 hours. So the index used was and the query ran for 7 minutes, so we tried implementing an index, that is day and user ID applied during self-join stage, but still it ran the full collection scan because day is a course bucket and thousands of docs matched per tweet, and the result was 3.4 million documents examined. We had to use index better, and we in real world scaling needs we could implement final grade indexes and materialized pre-joins. Is the output. The next question was cross promotion chains. Find cases where user A posted a domain within 2 minutes of the user B. I mentioned A. When we follow the strict 2-minute window, we got no results, and we extended the time to 10 minutes. It still got 0 results, and then when we extended 16-hour window, we got some results. Because initially we got no results because only 918 mentioned users were present in our data set, and then when we randomized August to September 2025, the timeline, it removed the natural bursts, and our data was too sparse. So here's the insight and reflection. There were some limitations, that is randomization weakened our fine-grained temporal analysis, and using indexing benefited runtime from minutes to seconds. Now coming to the fraud detection graph model. We construct a unified payment graph that links clients, stores, and transactions. We imported CSVs into a Neo4j desktop. We modeled the purchase and transfer as set type of transaction for in the future, if you have to add another labels, it will be easier to detect. Then we extend the model with next edges. We order client transaction temporarily and then that is first to last transactions. Then we also added frequent counterparty and suspicious counterparty. That is summarize high frequency or high value transfer links. How did I select the suspicious counterparty? The answer is here. Initially, when we selected frequency only, it was too noisy, so I added a threshold that is greater than 100 transaction for a minimum of 5 to 6 transaction should be flagged as spam. Otherwise, small transactions would also be flagged. Then I added a daily 50K limit for a single transaction and a lifetime of 2.5 million for it to be detected as spam. Now coming to the problems. In this case, we demonstrate how the developed graph data model was used to answer 4 fraud-related analytical queries. Highest spending clients in time window. Identify which clients spend the most on purchases between 10 a.m. to 14 a.m. Our approach was to use parameterized start and end times and then filter purchase nodes with absolute time property. And then we selected only positive transactions that were considered to avoid anomalies. For each client, total spending and transaction were aggregated and the top spending store per client was derived. And a dense RAG method handled ties. Uh, then we got this proper result, but initially the given query didn't have any results for that particular time frame. So after debugging, we selected this timeline to run the query and provided the following result. This query illustrates temporal filtering and ranking within the graph. It highlights customers with intense short-term activity, which is a potential red flag for fraudsters and coordinated purchase laundering. Next question was clients with largest negative cash flows. We found clients whose negative outgoing payments exceeded incoming transfers. We ran the query through each client and then calculated the outgoing and incoming values. We calculated the net balance, and the query also calculated each client's highest single outgoing transaction. This is specifically helpful to this distinguish routine spenders from potential bulk fund movers. So here was the output of the top 5 clients with the most negative cash flow. Then we move on to the third question, that is pass through funds to a suspicious seller. We detect clients who receive transfer shortly before spending at the seller goods, which can be the funnel for all the money laundering. The seller name, here is the following approach we followed, and we calculated a spending ratio percentage was derived, and only clients with more than 2 purchases and 5% received funds that was transferred to goods for retained. And here's the outcome that we got. So interpretation. Temporal linking of inbound and outbound flows exposes behavioral signatures of laundering or funnel activity that are invisible in static datasets. Coming to problem number 4, our goal was to create a relationship that connects order transaction. So we found all transactions for each client and then we ordered them by time. And here's the visualization of the result that we got. Coming to the final part of our analysis, fraud network analysis. Fraud detection via graph data size. We know that clients may share identifiers, etc. Our goal was to move beyond basic transaction detection and uncover hidden structures and indirect collaborations. The tools that we use were Neo4j GDS, Lovin, WCC, label propagation, PagerRank, checkout similarity, etc. We did it, the data set connected via shared identifiers and transfers, and we followed 3 progressive steps: detect dense fraud groups, analyze cross-boundary fund flows, and predict hidden collaborations. For the first problem, we built a heterogeneous projection. Clients linked to identifiers using email, phone, TFN, etc. We applied 2 community algorithms. That is, one is Lovin, which finds dense modular subgroups, account sharing multiple identifiers, And WCC, weakly connected components, that detects basic connected groups that even if they share one identifier, WCC will mark you as a connected group. And here's the results that we got. Next, the question, following money flow beyond fraud groups, we isolated cross-boundary transactions. And then we ran the top 10 recipients for total incoming amount. Sorry. The key idea was to follow the money leaving non-fraud rings and to a funnel which is unrelated to the fraud rings. The insight was funds consolidated through high-value boundary accounts. So building graph projections, we did this and the clients selected if they share greater than one identifier, then we added edge weight, that is number of shared identifiers, and if the edge weights are higher, we will classify them as more important. It's the visualization, and the question is for this particular question, why did I choose LPA instead of K-core? See, K-core is very specific. It only keeps nodes with very strong connections for fraud detection in later stages with client groups that are which have too many shared identifiers, etc. K-core will be better, but for early detection focus, LPA can quickly highlight emerging communities. And it doesn't require parameters, so you don't risk missing groups because you set K too high. So, coming to the final question, building a temporal time-aware graph of money flow. We consider a temporal projection line where relationships store both transaction value and timestamp, and each node was a client, each edge money sent at a specific time. This enables detection of when and how funds move between accounts, not just who connects to whom, which forms a foundation for dynamic fraud pattern analysis. As you know, fraudsters often use separate accounts to hide coordination. We use Jacquard similarity, which is we use node similarity algorithm in GTS to measure overlap in recipients and specifically the timing pattern. So if fraudsters use different accounts, but if they follow the same timeline and the recipients match, you could have a Jacquard similarity. And if the similarity, we follow the similarity score that is between 0 and 1, if it was higher, it means more alike transaction behavior. So this is the pre-visualization, and then after time slider, we got the following relations. Thank you all for your time. Have a great day and hope you enjoyed the presentation.